has been at our university quite a long time, actually retired, I guess, in spring of 2011, and has still been with our university since then, and we're pleased about that. After a long term as chair, he told me when I asked him to give this up that he would actually be glad at the chance to talk to the department about mathematics again. So without further ado, let's let him do that.
Great, thanks, Wesley. I am very happy. I am indeed very happy to have the opportunity to talk about mathematics and not about some of the administrative things that I had to talk with you about far too many times in the last 15 years. And so thank you for the invitation. The work that I'm going to talk about today was joint work with Robert Fitzgerald, who was my good friend and colleague in the department for over 30 years, and he is now my colleague in retirement.
Much better that way.
Much better that way. And I should warn you that my computer presentation here is a learning in retirement project. So bear with me if it doesn't behave exactly the way I think it might or could or should. So let's see. I press the button here. So I turn this on. I got that part. Now let's see. So you can see the title here, which is rather vague, and I'll kind of flesh it out as I go along and make sense of these terms. The beginning of the project goes back to probably 2004 sometime. I got from Math Reviews a copy of a paper of Vladimir Arnold to review. And you can tell from the title here that it was a rather broad-ranging paper on a whole lot of interconnected, interwoven topics in number theory, geometry, abstract algebra. What else is in there, Bob? I mean, almost everything.
Just relativity theory.
Relativity theory, yes, thank you. Right. Most of which was lost on me. I have to admit that I at least paid attention through the second line of the paper, and I came across the following amazing theorem. This is not a mysterious identity of our own Brian Arnold, but this is Vladimir. Make that clear up front. So here's the statement of the theorem. This happens 2 lines into the paper, and Arnold calls this the trigroup property, a word which I've never seen used in any other context before or since. So he takes a binary quadratic form, and he claims that the product of any 3 values taken on by that form is another value taken on by that form. A very simple statement about a very classical object. And these have been the subject of studies literally for centuries, these binary quadratic forms. Very old and classical topic in number theory. This is something that I had never seen written down before. And it becomes more mysterious when you read the rest of the theorem. Here's a formula. Well, that looked pretty mysterious, so I thought, oh good, I'm going to read the proof, and then I'll understand what makes this work. I've reproduced the proof verbatim from the paper. Here it is. He attributes it to Francesca Icardi. Now, Jurek talked a couple of weeks ago, he talked about a proof from the book. Well, this is the antithesis of a proof from the book. It's messy, it's computational, and when you get to the end, you gained absolutely no insight into what made the theorem work. Basically, he says, well, we have some formulas there, just plug all the stuff in. Plug all the stuff in on the right-hand side, plug all the stuff in on the left-hand side, multiply it all out. There's 52 terms on the left-hand side. Oh yeah, and there's 52 terms on the right-hand side, and they're all the same. QED. Okay, so I was disappointed, but it sort of makes you want to understand what in the world is going on. So the next thing I came across in the paper is the following. He says, well, sometimes, and he gives a couple of simple examples. He says, sometimes it's even the case that products of two numbers represented by a binary form is again represented by the form, but not always. In other words, sometimes that set of represented integers is a multiplicative, what we call a multiplicative semigroup. And he says, this is the quote, it's an interesting question to find for which forms do the values form semigroups and for which ones they don't. Well, I have to admit, when I ran across that, I assumed that either A, this is something that was already known to Gauss, a question that Gauss could have answered had he thought of it, which it probably is, or B, it's something that's completely trivial when you view it from some contemporary perspective. Well, it turned out that neither of those was exactly the case, and this has led to an interesting project that's involved a number of topics in number theory and algebra. And I want to just try to describe those for you a little bit today. The things that we came across, the results we were able to obtain, and the things that we're hoping to accomplish now that we have all this free time in our retirement. So I'm going to call forms with this property multiplicative forms. Arnold chose to call these perfect in his paper, which wasn't such a great choice because that's already a term that's in common usage for an unrelated concept. So this is what we settled on. We decided to call these multiplicative forms. So the problem is to in some way characterize the integral binary quadratic forms that have this nice property that their set of represented integers is actually closed under multiplication. So, are there such things? Why might we expect to find some? Well, here's an old example, kind of a prototype example to keep in mind. You take a look at the sum of two squares, the simplest example maybe of a binary quadratic form. You take a product of two sums of two squares, the result is again a sum of two squares. And in fact, you can express the new variables that you need on the right-hand side as linear expressions involving the original variables. Now this, by all accounts, is a very old identity. In fact, you find this in Andre We's book, Number Theory, An Approach Through History. He makes the argument that in fact this identity must have been known to Diophantus in the 3rd century. It certainly would not have been expressed in this algebraic form, but he makes this statement about 65 being expressible in two different ways as a sum of two squares, and he says because it's a product of 13 and 15, each of which is a sum of two squares. So at least conceptually, he seemed to be aware of the fact that a product of two sums of two squares was again a sum of two squares, and you have the options of the sign selections indicated there, and that gives you the two such representations. You can check that these are a choice of x, y, z, and t that will give you that. Now actually this does appear in this very explicit form in the writings of Fibonacci by 1225, along with a fairly elaborate proof. Incidentally, you might recognize that if you stare at it for a minute now. From a contemporary viewpoint, think about the things on the left-hand side as being the squares of norms of complex numbers. Just look at x plus iy, z plus it. These are the squares of their norms, and then what you get on the right-hand side is what you get when you multiply those two complex numbers. Okay, so let me be a little bit more precise about what all of this terminology means in general. A quadratic form is a homogeneous degree 2 polynomial. And to say that it's binary means that there's just the two variables that I'll denote by x and y, hopefully consistently as I go along. And by an integral one, I'll just mean that the coefficients, the a, b, and c, are integers. Now you can think about this as defining a function f that maps z2 to z. It takes a vector. Think of it taking a vector, those giving you your values that you plug in for x and y, and it'll produce an integer as the output. So what we're interested in studying is the image of that map in z. What can we say about that set of integers? The classical language is to say that an integer m is represented by f when you can substitute values, I call them alpha and beta here, in for the indeterminates x and y and produce that number m as the result. And the set of integers represented by f, I'm going to denote just by this notation df. The form is said to be positive definite if all these represented integers are positive, and it's primitive if the GCD of the coefficients is 1. Now, associated to a form like this is its discriminant. Actually, in the literature, there's various conventions. I'll just use the one. I'll take b squared minus 4ac for the discriminant one. Maybe the most natural thing to us. And this is going to be again an integer because a, b, and c are. It'll be congruent to 0 or 1 mod 4. And if f is positive definite, that is a negative integer. So for the remainder of the talk, when I say form, I'm always going to mean an integral binary quadratic form. Those will be the only forms that I'm going to talk about. Well, with one small exception that will be obvious, hopefully, when I get to it. And I'll assume that they're positive definite, although that's mostly for a matter of convenience. These results also hold for indefinite forms, but I wanted to be a little bit more concrete here, and it eliminates some differentiations in cases and so forth. So the first thing that we'll do is we'll define, using the action of SL2Z, we'll define an equivalence relation on the set of these forms. Defined as you see it there, you just let an element of SL2Z, it's a 2 by 2 integer matrix, just let that act on the vector of variables in the way that I've indicated there. And I'll use bracket F for the equivalence class under this relation. I'm just going to refer to these as equivalent, but in the literature you often see this referred to as proper equivalence because you're insisting that the determinant of the matrix be +1 instead of allowing plus or minus 1. And that becomes a distinction that you have to keep track of at various points. Well, equivalent forms have a lot of the same properties. In particular, it's easy to see that they have the same discriminant, and if we're interested in studying the representation of integers, it's important to know that they represent the same integers. You can, these are invertible integral transformations, and you can do the reverse the substitutions. The common represented value set, I'll just use D of that class bracket F. So again, just a little bit of notation. I'll let script F here denote the collection of all the primitive positive definite integral binary quadratic forms. So these will only be the primitive ones. And for a fixed discriminant delta, I'll use that F with a subscript delta to be the primitive ones with that discriminant. then what have we gained by this equivalence relation? Well, it's a fundamental fact that for any discriminant, that set consists of only finitely many equivalence classes. So it reduces us down to a finite set. Now, in fact, we can do a lot more thanks to the genius of Gauss. We have not only a finite set here, but we can define a binary operation on that set, which will actually make it into a finite abelian group. And it's that group structure that will be valuable for us as we go along. So I want to describe just a little bit. If you try to read this in Gauss, it's very tedious and very complicated, so I'm not going to present Gauss's original version of it. But I'll present a version of it that's the one that you find in most contemporary number theory books that's due to Dirichlet. So it builds on the following somewhat technical lemma. Suppose that you have two forms with coefficients as I've indicated them there, with the additional condition that the greatest common divisor of A and A prime, the leading coefficients, and B plus B prime over 2 is equal to 1. The fact that these have the same discriminant forces the parity of B and B prime to be the same, so that B plus B prime over 2 is actually an integer. Dirichlet referred to these as united forms if you had this additional GCD condition hold. And what you can show is that if you take one of these equivalence classes of forms, take two of these equivalence classes of forms, I can select from those equivalence classes a pair such that those are united in this sense. So I can use these two forms in order to hopefully define some operation that is defined on equivalence classes. So the technical lemma is you can find this integer capital B that satisfies a bunch of congruence conditions. So that's a little that's sort of on the level of an exercise for an elementary number theory class. All you need to know is a little bit about solving elementary congruences in the Chinese remainder theorem, and so this is it becomes then a little exercise to produce this capital B. And then magically, once you have capital B, you can produce a form capital F that's, I just call it the composition here. It's sometimes called the Dirichlet composition because there's many different versions of composition that you find in the literature. Is as you see it there. The leading coefficient is just the product of the leading coefficients of the united pair that you started with, F and G. And then the middle coefficient is this number capital B that you produced by solving these congruences. And then that last congruence there says that B squared minus delta over 4AA prime is actually an integer. So that third thing that doesn't look necessarily like it's an integer is an integer. So this is an integral quadratic form. And it's easy to see that it's rigged up so it has exactly the same discriminant delta as the ones that you started with. Now, why is this interesting for our purposes? Well, let's take a look. I just used capital C here for that number, that B squared minus delta over 4AA prime. Then what you can show is that that original united pair, this refers back to the F and G on the previous frame. You can show that the F is equivalent to another form which has the same leading coefficient, but now it has the middle coefficient, this new capital B that we found. And the same way for G, and then you just solve for what the y squared coefficient has to be, and you can see it there. Then what you get is a product formula, which says that here's something represented by F, multiplied times something represented by G. Sure enough, it's represented by this form that was defined to be the composition of F and G. And in fact, I wrote down here very explicit equation that shows you X, capital X, and capital Y in terms of the original variables and in terms of the coefficients of the forms. So let me just give you the upshot of what happens here. You take any negative integer that's 0 or 1 mod 4, so it's a candidate to be a discriminant. I'll use this script C delta, the script C delta, to denote the set of classes of the primitive forms that have that discriminant. Then this composition actually induces a well-defined binary operation on that finite set C delta, which makes it into an abelian group. There's a lot of stuff there to check. That's another bunch of exercises that will keep busy for a while to verify all of those things. But this is all very classical, and in essence goes back to Gauss. Now, actually, we get a little bit more, and let me continue on here. If you have an H that is in the class, the product class of two forms F and G, then in fact by this identity up above and using these the SL2Z equivalents, what you can see is that you get a bilinear map from Z2 cross Z2 into Z2 that gives you a formula of that kind that appears there written in vector form. So once again, what you see is that the product of something represented by F times something represented by G is represented by this something in this product class. So that's what I've boxed in there at the bottom. Okay, a couple remarks here. This is usually called the form class group of discriminant delta that we constructed here. The elements are these equivalence classes under SL2Z equivalence, and the operation is this one that I've just described as induced by the composition operation. Now, two things that will be interesting as we go forward here. The identity element is the class that consists of all the forms that represent 1. So they're easy to identify, and they're all in the same. Turns out that such forms are all in the same class. This is classically it's called the principal class in Gauss's language. And if you take a form F, the inverse class turns out to be the class of what's usually called the opposite form, F op there, that you get from F just by changing the sign of the XY coefficient. Okay?
Make sure I'm picturing the right object here. This form class group, is it finitely generated?
It's actually finite.
Finite.
It's actually finite. Once we use the SL2Z equivalence classes, cuts us down to a finite set.
Okay.
And then the operation actually is defined on those equivalence classes. So, and the other note there is that F op represents the same stuff as F does, just change the sign on one of the variables. And you'll get the same numbers represented by either F or the opposite. Let's see, I think I have a couple of historical asides here. Much of this, when you see it in contemporary papers, it's in the guise of the language of ideals in rings of algebraic integers, initiated by Dedekind in the 1870s. And in this particular case that we're looking at, this form class group is isomorphic to what's called the ideal class group of a suitable order in an imaginary quadratic field. And the other thing I wanted to just mention, there's lots and lots of ways to try to generalize this notion of composition, and there's many papers on that subject, but there's a very beautiful series of articles by Bhargava that appeared in the Annals from 2004. I think the last one was in 2008. There's 4 papers on what he calls higher composition laws, which is a really beautiful series of papers that has some very nice consequences. Bhargava was a student of Andrew Wiles at Princeton, and the title of his dissertation is Higher Composition Laws. So this was a series that came from that groundbreaking work in his dissertation. Very, very, very beautiful stuff. Okay, so let me come back to the questions at hand. How about the trigroup property? Well, now we have a one-line proof of the trigroup property. If I have R, S, and T for primitive forms. For imprimitive forms, I guess I need 2 lines. But anyway, I guess it depends how long the lines are. Right? A one-line proof, I guess. Anyway, this one really is. You'll see it. Okay. So R, S, and T are represented, then so's their product. Well, why is that? Well, R, S, and T are in DF, and DF is the same thing as D of F op. So they're in that product. Well, and then we said that the class of the opposite form is the inverse class. And we had that basic containment. The product of the 3 value sets there is contained in the value set of the product of the 3 things, the 3 classes, and now that's just F. So, okay, that's nice. Oh, now there's another thing we can see here, and actually Arnold made this observation as well. If a form represents 1, then not only does it have the trigroup property, like every form does, but actually in that case it has the semigroup property as well, because products of 2 elements will be in there. Take R to be equal to 1, and R, S, and T are numbers represented by the form, so ST is represented by the form. So it gives you at least some family of forms that are multiplicative in the sense that I'm talking about. But actually you can get a little bit more. Turns out that if the cube of the class of F is 1, I just used 1 here to be as the identity class in that group C delta. If that's the case, then F is multiplicative. This needs 1.5 lines, I guess, for the proof. I separated this out. The cube of the class of F being 1 means, well, either the square is F itself, or that's the case where F is the identity. Let that fly in here. Or if it's an element of order 3, then F squared is F inverse. Okay, so you have one or the other of those, and then if you take your product ST of 2 represented elements, it's contained in the represented value set for the square of the class of F, which sure enough, that's the class of F. Well, either F or its inverse, and they both represent the same values. So you get a sufficient condition at any rate for forms to be multiplicative. So this is what I referred to in the title of the talk. This is what would be called a 3 torsion element in the class group, an element whose cube gives you the identity. Well, it turns out that these also have a very long and interesting history and connect up with something that looks, at least at first glance, to be totally unrelated to what we're talking about. Well, marginally related, I guess. And that's appears, if I'm not mistaken, I think this is Eisenstein's first published paper in 1844 in Krill. And he looks at a correspondence which takes a binary cubic form now, one that is homogeneous of degree 3 of that particular type, and he associates to that a binary quadratic form whose coefficients are given by the peculiar equations there. The source, well, almost, of those equations is that you take, for that form capital F, you take the Hessian of F, so you take the You take the matrix of second partial derivatives, so it's a 2 by 2 matrix, and the entries there are going to be linear forms in the variables, in the x and y. So when you take the determinant of that, you're going to get a quadratic form in x and y. That's our binary quadratic form. And if you do the calculation, you'll see it comes out sort of to be this. There's a fudge factor. I think it's -1/36, if my memory serves me correctly, to get that. Okay? And then Eisenstein went on to observe that he looked at this correspondence. It takes f to the cubic form to a binary form. He noted that that commutes with the natural action of SL2Z on the variables in each case. And so it maps SL2Z equivalence classes of the binary cubic forms to our SL2Z equivalence classes of binary quadratic forms. Okay? So it's a natural question to ask what forms come up, which quadratic forms come up as images under this correspondence. And in fact, it turns out, this was Eisenstein's language, he observed that under some conditions that I've mentioned there, of a quadratic form, little q, arises in this way from a cubic form, if and only if, well, in his language, the triplication of Q gives the principal class, which was just a little flowery way to say, well, it's a 3 torsion element in the class group. So these mysteriously arise from this correspondence with binary cubic forms that was first investigated by Eisenstein, and then there are a number of papers that you can find in the literature on that topic. These other papers eliminate the conditions, the restrictions that Eisenstein worked under, and eventually you get a very nice complete generalization that appeared in 2000, where the forms are allowed to be forms they're not coefficients, they don't have coefficients in Z anymore, but suppose you allow any integral domain of coefficients, and what they show is that essentially this same correspondence works in that kind of a generality. So in particular, if you have a principal ideal domain, the elements, the binary forms that you see there that have their coefficients parametrized in that funny way by those equations that we saw before, turn out to be exactly those that correspond to the 3 torsion elements in the form class group. So it's a very general phenomenon. Okay, so let me go back to the problem at hand. Bob and I were able to determine a number of equivalent conditions for multiplicativity. I've stated them here for primitive forms. So the first one is that df is closed under multiplication. That's our condition that Arnold was interested in. The second one is that it gives rise to a 3 torsion element in the class group. Third one is that you get the coefficients of the form by a parametrization of the type that Eisenstein discovered. And the fourth one is that the multiplication formula arises in a very special way through a bilinear pairing that looks similar to what we saw in the composition operation. So these, just for the purpose of abbreviation, the first one, we call these multiplicative. The second is the 3 torsion condition. The third one, when these particular equations hold, I'll just say that the forms are, that the binary form is parametrizable, and I'll say it's normed in the last condition. So these are all equivalent. Actually, let me see. We've seen 2 implies 1 already. That was on a couple of slides ago. 2, if and only if 3, is basically this business with the binary cubic forms. And it's obvious that 4 implies 1. So there's a couple. The main missing ingredient is 1 implies 2, and that's what Bob and I were able to prove. Actually, it comes from a little bit more general criterion for multiplicativity. I'll state that in just a minute. That we published in the AMS proceedings in 2007. And it's also interesting, we can show that the equivalence of this condition 1 and 2 also holds if you look not just at products of 2 elements, but suppose you look at products of any even number of elements. So you look at k-fold products for any even number k, then that is related to the order of the class of F in the corresponding class group. So this character, we can characterize the odd order elements in the class group in terms of the property, closure property under k-fold products of their represented value set. Seems like there might also be some characterization for the even order elements, but it has so far eluded us. Another learning in retirement project, I guess. Anyway, the condition, that fourth one, was actually introduced in a paper by Icardi and Timmerin. There was a volume of the proceedings of the Steklov Institute that was dedicated to Arnold's 70th birthday in 2007, and this there's actually a very interesting article by Icardi and Timmerin where they study that condition, and they're actually able to characterize all the circumstances under which you have one of those bilinear pairings that gives rise to a multiplicative formula of that kind. And they conjecture in their paper that this is in fact equivalent to condition number 1. The proof of 3 implies 4, I'll mention this just because I want to refer back to it in a minute. Once you have that parametrization, you can just write down this bilinear pairing which satisfies condition number 4. That's another a non-proof from the book. You just write it down and you check it and say, ooh, hey, it works. Okay, so that gives a reasonable picture, at least, of the case for primitive form. It kind of connects with a number of different, maybe what were not initially obviously related topics. What about imprimitive forms? Well, in this case, I'll write them like this. Take an F, and then let just for a notation, let little d be the GCD of the coefficients, and factor that thing out, and then you have some primitive part that's left after you've factored out the GCD out of all the coefficients. And I just called that F hat, so that guy's primitive. Now, here's the other line that you need in order to extend the trigroup property to the case of imprimitive forms. I don't think I'll go through that, but basically you just factor the d out of all the integers that you're trying to represent, and then you use the trigroup property for the primitive part, and then you introduce the factors back in, and you can see there's not much involved there. Now, Arnold, in his paper, observed that if you take the form 2x squared plus 2y squared, that is a multiplicative form in the sense that we're using, but 3x squared plus 3y squared is not multiplicative. Well, that's easy to see because it represents 3, but it doesn't represent 9, 3 times 3, because 3 is not a sum of 2 squares. So it's easy to see that that's ruled out. But these two guys have the same primitive part. They just have different GCDs of their coefficients. Once you factor those out, you get the same primitive part. So this was the criterion that we obtained for multiplicativity. In general, the form f is multiplicative if and only if that number d, that GCD of the coefficients, either is represented by the primitive part of f, or it's represented by the cube of the class defined by that primitive part. It turns out if you only look at examples of the kind that Arnold had here, where you don't have an xy term, then in fact you only need the first condition there. The form multiplicative if and only if the d is represented by the primitive part, the f hat. That's because f hat cubed, that class is just equal to f hat in the case of these diagonal forms where the cross-term coefficient is 0. But it turns out that you do actually need that cube. So in particular, that 2x squared plus 2y squared is multiplicative just because 2 is a sum of 2 squares. But you do actually need that other condition. It comes up, for example, here's one that does have a cross term. That guy is multiplicative. Its GCD of the coefficients is 3. 3 is not represented by the form itself, but it is represented by the cube of the class. So this guy is multiplicative. So in general, we observed that parametrizable implies normed, implies multiplicative. All that works as we observed for imprimitive forms as well as for primitive ones. And there were two conjectures. Eicardi conjectured one of those reverse implications. He conjectured that multiplicative implies parametrizable. In a paper in 2004. So he was conjecturing that every multiplicative form arose from one of these parametrizations. And in that paper of Eicardi and Timorin that I mentioned earlier, it's conjectured that multiplicative implies normed, so that the only time you can have a multiplicative property is if it arises from one of these bilinear pairings. Well, it turns out we found out that this one is, the first one is false. And here's a counterexample, fairly easy one. That guy is multiplicative, but we worked out some relatively simple criteria whereby you can check parametrizability, and this one, it's easy to check using those criteria. It fails that test. The second one, it turns out that one is true. We're able to prove that in general you do have multiplicative implies norm. In fact, we're able to do that a little bit more generally by looking at these k-fold products. Anytime you have a k-fold multiplication, you have also, it comes from a k-linear map from k copies of Z2 into Z2. So pretty straightforward generalization. So the question remains, I guess, what happens to, what forms can be multiplicative but not parametrizable? So one might ask this question, start with a primitive one, let's say, and then look at the things that are represented, the R's that are represented by that, and look at the forms RF. For which of those do you get parametrizability? And we started to look at some examples, just kind of randomly, and we discovered that in fact there was a considerable difference depending on the primitive form that you started with. Sometimes it appeared that everything that we checked would turn out to be parametrizable, and other times there was a mix where many of them were not parametrizable. It's easy to show, incidentally, there's always infinitely many R's for which RF is parametrizable. That's not hard to do. But it turns out that this leads to something else that's rather interesting when you try to distinguish which cases are which. You run into not the 3 torsion elements in the class group, but the 4 torsion elements in the class group. It turns out that if the 4th power is 1 in the class group, then in fact, these are the cases that RF is parametrizable for every R in DF. And if this isn't the case, the 4th power is not 1, then in fact PF is never parametrizable for any prime that's represented by F. It will be parametrizable for some composites, not for others. I don't know if there's a nice criterion to distinguish which are which. We kind of looked at enough examples to convince ourselves that that was kind of a mess, and maybe that's not really worth trying to pursue too much, but it's interesting, or we thought it was interesting anyway, that these 4 torsion elements are exactly the distinguishing factor here. So let me just close with a couple of further questions. The first one actually goes back to Arnold's original paper. He asked the question of what proportion of triple. Look at R3. Look at the integer lattice points in R3. They correspond to binary quadratic forms. Just take triple ABC and associate it to ax squared plus bxy plus cy squared. So you can ask the question, what is the proportion of triples in a large cube or a large ball or whatever is most accessible? What's the proportion of those that are that correspond to multiplicative forms? Is there some sort of an asymptotic formula? Interesting question. We don't know the answer. There's some numerical data out there. In fact, Arnold had done some numerical calculation already before his original paper. He was looking at about 20% up to the range of values that he was able to check without too much effort. And Icardi also has some bit more extensive computer experimentation of some values too, but that general problem is still open. Second one is a question that Peter Morey wrote to me and inquired, under what conditions is F on F is DF a multiplicative set? Well, I was kind of careless, and so my response was, well, didn't you read our paper? And he says, oh no, I mean a multiplicative set, not a multiplicative semigroup. So in the number theoretic sense, a multiplicative set of integers is a set that's closed under multiplication of relatively prime pairs of integers. I don't know the answer. I looked a little bit for some examples. I couldn't even find any examples of a case where you might have a form for which DF is a multiplicative set without actually being a semigroup. It's not too hard to show that if you had such a thing, it would have to, its 6th power would have to be the identity in the class group. So this would have to be a 6th torsion element. So I bravely looked for a few elements that whose 6th power is the identity, but whose cube wasn't, and just take the first couple of primes that you could find that it represents almost every time their product isn't. So I have no feel for this at all. As to whether there are such things or how you might prove that something has that property. And a third question, just kind of a word-ended question. What happens if you replace Z, the coefficient ring, by a general integral domain or an integral domain with some other nice properties, whatever they might be? How much of these things will extend? I commented earlier on that nice paper of Hoffman and Morales, where they talk about this the three torsion condition and the parametrizability form that holds over a general principal ideal domain. Bob and I were able to show that this trigroup property holds pretty generally, appropriately formulated for binary quadratic classes over any old Dedekind domain, for instance. So there are some more learning and retirement problems. I want to thank all of you for your attention. I want to thank Bob for an interesting collaboration on this problem through the years, and hopefully we'll be able to do a little bit more. Thank you.
Other questions? I have one. There's a whole lot of semigroups in the world, and these seem like pretty rigid conditions. Which semigroups do you get? Can you say anything structural about the semigroups you get in this way?
I don't know. I don't know. We really did not.
I mean, they're all infinite, so there's that much structure for infinite.
They're infinite, yeah.
Oh, but still, you could say things about the generation. It wouldn't surprise me to know that they all had to be finitely generated.
Oh, I'd be real surprised with that. Now, they represent infinitely many primes, so I would think they're infinitely generated.
It could be. It wouldn't. It would surprise me to know that any of them can be star-free.
I don't know what that means. So
Yeah.
I guess that would be surprising.
On that note, is there anything you can say about the ideal structure of the semigroups? I mean, is there any obvious ideal structure in the semigroups?
In the semigroups?
Yeah.
Well, I mean, to some extent, I mean, I guess you can. I mean, you have multiples of primes in there, for example. So I suppose you certainly have a wealth of ideals. What you can say beyond that's useful, I don't know. But certainly, yeah, there's lots of ideals in there.
So I have a question to Greg. Do you think Ries's theorem would apply?
Yeah, well, that's the thing. That's the first thing you think about is something like a Ries's theorem. But I mean, then it's not clear you could put a topology on it where something like a Ries's theorem you would have. Sort of kind of minimal ideal of some sort.
Worth looking at.
Yeah.
We'll talk.
Yeah. Sure.
Anything else? Before we thank the speaker again, I'll remind folks that there are refreshments up on the third floor. Thank you.
Thank you.